Okay, welcome again to the 2021 UC Davis Tahoe Environmental Research Center Docent Training. I am very excited to welcome to present to us Annie Kell, who is our one of our favorite geologists next to Francis Pierce, who's our other favorite geologist. And Annie has some kids in the background there. It looks like getting chewed away. And I am going to go ahead and spotlight you, Annie, and then you'll be able to share your screen. And so you are up.
Hi. Hi. So yeah, thanks for having me. Yeah, this year, I don't know if you've seen the, you can look it up on YouTube and it's hysterical. It's this guy, he's on a live interview on BBC and his kid comes into the room followed by the baby in her walker, followed by the mom like grabbing them both, like and hauling them out of the room. But that has definitely been, that's like been my life for the past year. So it's really funny, you should look it up. But here, I'll go ahead and share my screen. And oops, here we go. And go play. And so if you guys have questions as we're going along, feel free. I'm going to close the chat just because it takes up real estate on the screen. But if you have a question, you know, feel free to shout it out or whatever, and ask, or maybe I'll see the blinky thing if a chat comes up, but you know, feel free to ask questions as we go along. So my name is Annie Kell and I am a seismologist. So I study earthquake faults, and some of my research is in Southern California, but then I've also done a lot of work here in sort of Northern Nevada and in the region where Lake Tahoe is. And so hopefully everybody, I kind of like this picture. It did cut off my email a little bit. It's just annie.kell@gmail.com if you want to get in touch with me later. But just a good reminder, because we live in earthquake country, just remember what to do if there's an earthquake. Drop cover and hold on. It's always a good reminder. Oh wait, hold on. Maybe I can try to keep the chat open. Okay, so this is going to be
the chat for you, Annie.
Oh, cool, great. So this is a geologic history of the Lake Tahoe Basin. Okay, so the things that we're going to cover here is starting with the very like long-term geologic history of the Western U.S. in general, which basically includes the formation of the Sierra Nevada, the initiation of basin and range faulting, and the very beginnings of Lake Tahoe. And then we'll look more specifically at the geology of Lake Tahoe, which are the faults that are within the lake, how they're studied, some of the different glaciations and what influence they had on our beautiful lake, and then some of the more major geomorphic events of Lake Tahoe. So this image is a geologic map of Tahoe, and it shows a lot of the different geologic units, and then these solid lines are some of the more dominant faults, and then the dashed lines are other mapped faults that are more splays of the larger faults, but we'll get into that in more detail. Oops. Okay, so just a reminder of the geologic timescale. If I throw out some of these words, all it basically means is a period of time. And so there is very, very, very old time, Precambrian, which is basically from 1 billion to 5 billion years ago. There's the Paleozoic, which is like basically like 500 million years ago to about 200 million years ago, and then so forth. And then we live right here. We live up here in the Holocene, which is our period is the Quaternary, and then we are in this very small epoch of the Holocene. So that's where we live now. But each of these represent different time spans and major events, or they're punctuated by different events, or maybe different mass extinctions or things like that. So, but if I throw out some of these words, that's all that really means. Okay, we can come back to that if we need to. So, pre-Mesozoic, which means pre-250 million years ago, the Western US was mostly covered in shallow marine continental shelf. So it's a shallow ocean environment. And then it also went through to some deeper marine deposits. So this brown area on this image on the right, this is the North American craton, which is essentially, it's basically continent that hasn't deformed in like a billion years. Basically, it's very, very much not deformed in a very, very long time. There is a section of craton that has been deformed, and that includes some of Western Nevada and then the Colorado Plateau and so forth. And then we have this green area that is an accretionary belt where there has been a lot of volcanism and tectonic activity and convergent plate boundaries and different things like that. So up until about 250 million years ago, this area was shallow ocean. Okay. From about 100 million years ago until about 20 million years ago, the Western US was a convergent plate boundary. So two plates were colliding with each other. Those two plates were the Farallon plate, okay, which was moving towards the east, and then the North American plate, which is, we consider the North American plate to be stable, so it doesn't actually move a whole lot, but it would be moving west, like relative to the Farallon plate. Okay, so the Farallon plate was subducting beneath the North American plate. And that caused a lot of really interesting things. Like for one, it is the initiation of the volcanism that formed the Sierra Nevada batholith. A batholith is like it was formed underground, but it's a lot of magma intrusions that occurred over the whole length of the Sierra Nevada and have since been exposed in our amazing mountain range. And it also is responsible for some of the uplift of the Colorado Plateau. And then the mountain ranges that are in eastern Nevada called the Sevier range. And then beginning about 80 million years ago, the way that the volcanism behaved in Nevada changed. And that more than likely is due to a change in like the geometry of how that slab was going underneath. But there's a lot of sort of contentious research on that particular topic. But that caused volcanism to sweep across the rest of Nevada. Okay, so for a very long time, it was focused in the western portion of Nevada, eastern California, forming the Sierra Nevada batholith. And beginning at about 80 million years ago, the volcanism changed across the rest of Nevada. Oops. Okay, so this is kind of a cool diagram. It looks really complicated, but we'll step through it. So it's actually much, much less complicated and pretty interesting when you look at it. So at about 30 million years ago, the Farallon plate fully subducted, okay? So this image here on the top is showing a snapshot of what the tectonics looked like and kind of a rough diagram of what the states would have looked like 20 million years ago, okay? As we go down, we go through to 15 million years ago, 12 million, 5 million years ago. This one, block E, is current day. And then F is an extrapolation as to what the tectonics are likely going to look like in 7 million years from now, okay? So at about 30 million years ago, the Farallon plate completely subducted, okay? And when it subducted, it was sort of grabbed by this other moving plate up here, the Juan de Fuca plate, and it initiated this lateral motion, the side to side shear motion, which it became eventually became the San Andreas Fault. Okay, so the San Andreas Fault began about 20 million years ago. Okay, and over time, it continued to lengthen, extending down into this area here, which is the Baja Peninsula, and later became over here the Gulf of California. So you can see here, this red line is the San Andreas Fault. And this kind of red zigzaggy line, this is in the Gulf of California. Okay, and then this part right here is the Baja Peninsula. Okay, so today this system is very, very active and influences our local tectonics pretty, has a pretty big impact. So we have the San Andreas Fault here. And a lot of people think of a fault system as being, you know, one exact location. Like the San Andreas Fault is, it runs in this, you know, centimeter wide strip all the way up the length of California. But in reality, fault systems are pretty diffuse, and they spread that motion out across sometimes different fault splays, sometimes entire different fault systems. So in the case of our Pacific plate boundary, about 75 to 80% of the relative motion between the Pacific plate and the North American plate, about 75 to 80% of that motion is focused on the San Andreas Fault. The other 20 to 25% is in this kind of white, this region that's highlighted here in white, which is called the Walker Lane Belt, or the Eastern California Shear Zone. So this region, the Walker Lane, extends from Southern California about where there's a fault called the Garlock Fault. And then it extends north up to about Honey Lake, which is about maybe 60 miles north of Reno. Okay, so Tahoe is within the Walker Lane Belt. Okay, and that is kind of the basis of our tectonics for Eastern California and specifically the Tahoe Basin. Okay, so with part of this like larger tectonic system, about 20 million years ago, it began to open and pull wider to spread this area that is Nevada and the Basin and Range. Okay, so the faulting, the spreading zone, the divergence of the crust in the Great Basin began about 20 million years ago. Okay. Okay, so currently our tectonic setting is this. You know, we have the North American plate, which is really pretty stable. All of these different arrows show the direction of the plate movement, and then the longer the arrow is, it indicates a faster velocity of movement. So the North American plate doesn't have a whole lot of movement. It's relatively stable. And the Pacific plate is moving at a very rapid rate to the northwest, okay? So that is still initiating motion along the San Andreas Fault and is still responsible for some of the Basin and Range faulting that we see. Okay, so here's a little bit more on the Walker Lane, and then a zoom in on just, you know, the region here between Tahoe and Honey Lake. Okay, so again, about 30 million years ago, the Farallon plate subducted fully. It started to, when there was a collision with the North American plate and the Pacific plate, there began to be a motion to the northwest, which caused the strike slip fault of the San Andreas Fault and also started to pull apart the crust of the Great Basin. Okay, so the fault systems in our region are indicate that. So they're both what are called normal faulting, okay, which is mountain building faults that go up and down, and they're side to side faulting. So they're strike slip. So they move in the direction like the San Andreas is moving, which is called a right lateral system. So a lot of our faults in our region are a combination of those two types of motions. A general rule of thumb when we're looking at faults in Western Nevada is if the fault is moving mostly north-south, like for example, this fault on the east side of Pyramid Lake, that's a normal fault. So one of the up and down faults, okay? And then in general, if a fault is kind of directed up towards the northwest, that's one of those strike slip faults or right lateral faults, okay? Hold on just a moment. You can take your charger. You need to go to a different room. Okay. Okay, so there's a lot of confusion about, or at least I feel like something that I have to reiterate when talking to people at times is the difference between the Great Basin or the Basin and Range and the Walker Lane Belt. So the Great Basin is our geologic region where everything is flowing, you know, inland. and not flowing to the Pacific Ocean, okay? The tectonic settings between the basin and range, which is the eastern portion of the Great Basin, and then the tectonics of the Walker Lane are very, very different. So these blue lines show geodetic measurements between the Wasatch Range in Utah and the Sierra Nevadas. Okay, so again, the arrows show the direction of motion, and then the length of the arrow indicates how fast that tectonic strain is. So from the Wasatch Range to central Nevada, you can see that the motion is directed mostly to the west. Okay, so it's pulling apart. Okay, and it's a relatively low strain rate. However, when you get into more western Nevada, eastern California, the direction of the strain changes to pick up that northward motion, such as what the San Andreas displays. And then also the magnitude of motion increases significantly. So it changes our seismic hazard in this region, and also, you know, changes the types of faults that we see in our region. Okay. So the faulting in Lake Tahoe specifically began 2 to 3 million years ago. Okay, so that actually every time that actually really blows my mind that the faulting in Tahoe is only 2 to 3 million years old. It seems really, really young. Okay, so the oops, oh no, what has just happened? Did it just crash? Hold on. Keynote crashed. Okay. Come on, Keynote. Don't fail me now. Okay, hopefully it's back. Okay. So the Lake Tahoe Basin itself, the basin was formed by block faulting, and then the shorelines were shaped by glaciations, which I'll get into in a little bit. Okay. So block faulting is what is called a normal fault, where there is what is called a footwall, okay, and then the hanging wall. So what happens in block faulting is the footwall goes up relative to the hanging wall. The hanging wall drops down relative to the footwall. And over many, 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 many earthquake cycles, it ends up forming a depression up against the fault plane. Okay, and it forms a basin that can, you know, has in the case of Lake Tahoe, is filled with water. Tahoe is actually a combination of 3 normal faults, okay? Oh my gosh. Hold on, let me just see if I can just close everything. Let me quit everything I have on my computer. And cancel, iTunes, who has iTunes? Cancel, quit. Reopen. Okay, sorry guys.
No worries. It is flexibility in our word. We're good with it.
It's like, welcome to
my Zoom freezes up and just kicks me off occasionally. So
gosh, it's such a nightmare. I'm so ready to be with like Zoom everything. Okay, so there are 3 normal faults in Lake Tahoe, which are dropping down, progressively dropping to the, let me see, I'm gonna open, okay, was that, I'm not sure what's happening now, actually. Deep breath, computer, you can do this. Okay, they are progressively dipping to the east, okay? So what that means, oh my Lord. Okay, I'm gonna go ahead, you know what I'm gonna do is I'm gonna export it as a PDF. I'm gonna stop my share super quick, export it as a PDF, and then try to pull it back up only when I have a video to show, or I can just open that video probably.
the embedded videos are always causing problems, aren't they?
You know, they're usually better in, I feel like it's usually Keynote does okay with them. So
It's the combination of Zoom and Keynote. I have a problem with Zoom and PowerPoint together.
Okay, I'm gonna give you one more time, Keynote. Otherwise, you're gonna be fired. Okay, so okay, Keynote's fired, and let me find. Okay, I'm gonna re-share my screen. Okay. Okay, so you guys can see this now. Okay.
Yes.
Okay, so the deformation, the amount of like vertical. I hate this so much. Hold on. Open. Oh, I'm okay. Okay. Oh my Lord, this is just a disaster. What is happening here? Open with preview. You get kicked you guys off, right? Okay. Yeah. The amount of deformation that has occurred along the eastern flank of the lake is actually, it's dropped down deeper than the deformation on the western shoreline. So for example, if you can think of, if anybody knows of Cave Rock, which is, where is it? Probably about right here. Cave Rock is a volcanic neck. And over on the west shore, there is Eagle Rock. Well, those two volcanic necks formed at the same time. But when you compare wave cut terraces, like the kind of the shoreline cuts that occurred at the same time, it is the vertical displacement of Cave Rock is much, much more. I think it's on the order of like 10 meters more than it is on Eagle Rock on the west shore. Okay. The deepest part of Lake Tahoe, which is just over here off of the tip of Brockway Point, is tectonically controlled, and it is due to one of these vertically dropping normal faults. Okay. Okay, so that faulting began about 2 to 3 million years ago, and it continues to this day. So did anybody feel the earthquakes that have happened over the last few weeks? It's kind of interesting. We can digress.
Oh, definitely.
Okay, we can digress for a split second. Okay, this does not quite show it, but there was a magnitude 5 basically about right here in a lake that is called Independence Lake, and which is a really amazing place. If you haven't been there, you should definitely make a day trip out there. But the fault that runs through Independence Lake is the current research is assessing whether it is not whether or not it actually is a linkage between to the West Tahoe Fault, which is kind of interesting. Then the other earthquakes that have occurred in the last few weeks, they've been in the magnitude 3 and up to about a magnitude 4 range, have occurred on this North Tahoe, the state line North Tahoe Fault, which is this red one right here. And some of them have been very, very strike slip, so side to side, and then some of them have been have a little bit of a vertical component. Okay, so while that faulting was going on, as it is still going on to this day, we also had glaciations that occurred in the all along the crest of the Sierra Nevadas. Okay? There were 3 major glaciations that occurred in the Sierra Nevadas. There was the Tahoe glaciation, which was about 70,000 years ago. The Tenaya glaciation, which was pretty small, so it didn't have like a major impact on my dog's name is Tenaya. She just looked at me. I didn't have a major impact on shaping the shorelines. And then there was the Tioga glaciation, which was glaciers that were present between about 30,000 and 10,000 years ago. So this blue area indicates the last glacial maximum. So up until about 10,000 years ago, the crest of the Sierra Nevada was capped with a pretty large expanse of glaciers, okay? So while the basin of Tahoe itself, the hole that was filled with water, was created because of earthquake motion, tectonic motion, the shorelines, which are so beautiful and really interesting and unique, were sculpted by moving glaciers. Okay, so we'll get into a little bit of that now. Okay, is that the correct? Okay, so one thing that's kind of interesting is the way that glaciers impacted lake level, because I teach the Geology 100 class at UNR, and one of the questions that I have on the test is about how during glacial maximum sea level goes down because all of that water is not making its way back to the ocean as quickly, rather it's being locked up in these large glaciers on land. However, in Tahoe, the lake level is higher during glaciation. So it's sort of a backwards thinking. And the reason for that is because the outflow was blocked by a glacier. Okay, so the outflow of the Truckee River was blocked by ice during the glacial maximums. And so the lake level went up. Those lake levels going up have left indications of the various lake levels around the lake. And that is what is seen in these kind of sketched out lines along here. You can see, a red line, green line, and so forth. And it shows some of the different heights of the lake during these different glacial periods. Okay. So there is a lot of remnant geomorphology of glacial activity in Lake Tahoe, okay? And the two really interesting ones are the types of moraines. There are lateral moraines and then what are called end moraines. So when a glacier is moving downhill, it basically bulldozes all of the sediment. It carries with it massive, huge rocks. But it also bulldozes all of the sediment and smaller rocks at the front of the glacier and along the sides of the glacier. So if we imagine this glacier moving in this cartoon up above, if you imagine this glacier moving downhill, it pushes all of this material out in front of it, okay? Then as that glacier recedes, well, the ice melts back, but all of that material, all of that sediment and debris stays in place, okay? And as it continues to regress, it leaves what are called recessional moraines. So it's moraines that indicate the regression of the glacier, okay? On the side, it does a similar kind of bulldozing thing, and those are called lateral moraines. So here, if you can see this kind of tiny corner over here of Fallen Leaf Lake, and you can see all of these lines in this direction. Well, those are all the recessional moraines from the last glacier that was in the Tahoe Basin. Okay. Similarly, Cascade Lake itself and Emerald Bay were cut into the granite rock because of a glacier moving downhill. So most of the Lake Tahoe Basin was tectonically formed, but Emerald Bay itself is actually cut out due to a glacier. Okay. So this is a lateral moraine right here. Actually, here's something really cool. So if everybody here is probably driven all the way around the lake, right? And so when you come, you can kind of see the road right here along the west side of Emerald Bay. And then if you can think of that crazy like knife edge scary road that you have to do a switchback on when you're up above Cascade Lake, well, that you're actually driving right on the peak of a lateral moraine. Okay, so this lateral moraine right here has the highway on it. Okay. Okay, this also shows the location of the West Tahoe Fault. You can kind of see it here along the base of Mount Talac, but I'll show a little bit more about that in a moment. So West Shore also has some really striking lateral moraines. Here you can see these ones along Meeks Bay and into McKinney Bay. And these are also cut by some faulting activity. And that's actually kind of, it gives a lot of good information because we know about the age that these moraines formed. We can tell how long it took for this offset to occur because of the fault activity. So this 25 meters of offset has occurred in about the last 30,000 years. So hopefully when we're looking at something like this, you can kind of see the 3D nature of it. So in this bottom image, we're looking down at two different types of geophysical data. This black and gray imagery is what is called LIDAR, which stands for light detection and ranging. So they, the data are collected by going out in airplanes and like shooting lasers down at the ground from a bunch of different angles of incidence. And it's just a huge, huge, dense coverage of returned laser pulses. And through processing, you're able to take away all of the trees, all of the hills, all of the houses, and any of anything that you're not interested in, and you're left with is called the bare earth model. And so when we're looking at this, we can see the roads, but the rest of it has had all of the trees stripped out of it. And the reason that that's really useful to us is that it obscures the trees and all the shrubbery and things like that, obscure the location of the fault. And even to the point where, I've been standing in Tahoe, like looking at the LIDAR going, okay, I know I'm standing right here and there's a very prominent fault scarp, but because of all the manzanita trees and all the different shrubberies and things like that, it's very, very, very hard to see it. So LIDAR is useful in imaging fault structures on land. The stuff in the lake is a different type of data that are very similar. It's called bathymetry, and it's collected on a boat, and it's a sound pulse instead of a laser. But it is it's the same type of idea where the pulse is sent out, thousands and thousands of times, and then the return is processed, and it gives a really detailed look at the topography beneath the water on the bed of the lake or the bed of the ocean. Okay, so these images have put those two things together, so we can see the transition of features and fault offsets and things like that on land, and then how they kind of transition into the more marine environments. Okay. So, and the way that the shading on this is, it's so in this bottom one, the lighter colors are what are further away, lower elevation, and then the darker colors reflect both the angle that the light is coming from, but then also the elevation. So hopefully you guys can look at that and kind of get a grip of what we're seeing, okay? Okay, so by using bathymetry in Tahoe, researchers, I think in the 90s, discovered something really, really interesting, which is that the bottom of Lake Tahoe is not flat, but in fact, it has these huge blocks of material. And I mean, this block of rubble is, it's got to be the size of, I don't know, like the size of an entire building on the UC Davis campus or something like that. They're huge blocks of material. So you can also—
one of them is as big as the Golden Gate Bridge.
Oh, okay. So here you can see these kind of submarine kind of landslides, the way that these are kind of slumping down, and you can see these underwater channels of where debris has slid down. And then you can also see this giant fan array of sediment. So what that is actually from is from a submarine landslide that occurred about 60,000 years ago. And it was a shelf collapse of all of this material in McKinney Bay. So if you're looking at this imagery, you can see that this is in the lake, and so the lake shore would be kind of along right here. So this is shallow material in the lake. This is shallow material in the lake as we get up to Dollar Point. And if you can imagine, this entire region of the West Shore was that shallow material with this steep slope on the eastern side. And that steep slope is controlled by the location of the West Tahoe Fault, okay? And so about 60,000 years ago, this entire shallow shelf collapsed and dumped thousands of square feet of material into the middle of the lake. Okay, so probably everybody has seen this video, but it's worth giving keynote one final prayer for for working to try to get it to play. I don't want to update. Okay, here we go. Work keynote. Okay, so as that shelf collapsed, it causes, just like a tsunami in the ocean or a landslide in the ocean, it causes a pulse of water. And the white colors are like the wave peaks and the purple are the wave troughs. You can see here, this is this airport in South Shore. And you can see how high, this is superimposed on modern day topography, but you can see how high the wave run up happened over the course of 15 minutes after the shelf collapsed. This has been modeled looking at tsunami-like deposits all the way around the lake. Okay, so this is going to show it from the different angles. So Incline Village is now here and McKinney Bay collapsed. So within about 4 minutes or so, the first wave pulse hits Lakeshore Boulevard. And this run up right there goes to about where Country Club meets 431. And then this wave, it's called a Seiche wave, when it's a resonating wave in a small basin like this. The Seiche wave continued for a very, very, very long time, much longer than the shaking from an earthquake or the shaking from the actual shelf collapsed. Okay, so maybe I'll see if I don't have to go back to preview. Okay, so